would you like me to share my screen or?
Hang on, let me see. There's 2 comments.
Okay.
Okay, Stuart Kelvin says, hello, George. Hello, Karen. Hello. And
hello, everybody.
Hello, everybody. We're about to get started. As the bio that was published was something I am not going to reread right now, but this is Dr. Hassina Bilheux. She works at Oak Ridge National Lab, and she is one of the best image processors we have in our industry right now. And she has graciously said that she would share some tips and some information and everything else, and a little bit about what she's working on at Oak Ridge as far as problem solving that could help you guys. So without further ado, Hassina, please take it away.
Thank you. Thank you, Karen and George, for this opportunity. It's always a pleasure to participate to your activities, and thank you for trusting me with expertise in digital image processing. I don't know how much I know. I feel like I learn every time. So, but can you see my screen?
Yes.
Okay, and I will get the laser pointer. Awesome. All right. So if you hear crying, it's my dogs. They are at my office door. They want to come in, but I prefer to keep them outside so they don't start barking during the presentation. So I apologize for that. So today, as Karen mentioned, I'm going to focus on some digital image processing. I want to give you a very broad view of what I do and how things work and the things I've learned through the years to check that the processing is you know, doing what I expect it to do. So, oops. Yes, the outline of my talk, I will go to digital, talk about a little bit about a digital image, the processing, and the real challenge we have today in the field is that we have data size and rate that we need to consider nowadays with the advances of detector technology. And then I'll go through a few examples and show you why we care about the histogram, what we do with it, why there is an advantage to do binning, filtering, and also a little bit of visualization and segmentation. And I'm very open to suggestions. You know, there are things you want to hear next time or a specific problem you have and you're able to you know, share some of the data. You know, I'm happy to help you and take a look at it and hopefully collaborate with you. So this is where I work. So I started at the high flux isotope reactor, which was built in the late 50s, early 60s. So it's a neutron source, and we do neutron scattering and imaging research. So we have an imaging beamline there that you can see here, where so imaging instruments with neutrons are very large scale. So these are not benchtop instruments. They are very focused on fundamental research. We also do industry research at these beamlines. So you can see here the facility where you see how neutrons fly from the reactor to the detector area, which is kind of hidden here behind the sample changer. And a few years ago, I moved to the spallation neutron source where I'm building an instrument, so this is CG1D, called Venus. And this is a large-scale project that takes a few years to put together. And we will have very unique capabilities, which I will highlight in a minute. So we can use the spallation neutron source today, which is using an instrument called SNAP. It's a diffractometer, but that's where we do our imaging. So what I'm focusing this coming years, and I think it's probably relevant to industry in general, is that I'm looking at using time-of-flight neutrons to look at strain. So if you put a sample in a beam, in this case, the sample was in the furnace, and you can measure through the sample thickness, you can get strain maps because you're able to measure what we call Bragg edges, which basically define the HKLs. And as these D spacing moves, these lattice parameters move due to heat in this case, you can see the changes as they are happening. So it's a pretty powerful technique. It's pretty involved, but it has a lot of applications in additive manufacturing, which in case was Inconel 625, but also welding. You could image a weld as you're welding, like friction stir welding at the beamline, and see what's happening to your materials. So what we have done in this case, we've relaxed the strain. So this was to see how high of a temperature do you need to go, how long do you need to expose the sample to the temperature. And that's very important for companies because they can use this to model their heat cycles for the annealing process. So here's the Venus instrument, which is currently under construction. So you can see we get a ton of rebar delivered last week. We have a detector at about 27 yards. The neutrons are coming this way. We have a large cave that we're building with HD concrete. And the reason why we have a large cave is because our instrumentation is quite involved. You can see here the floor space we're taking. This is at the reactor. We're doing some polarized imaging where you can use neutrons as little magnets, and you can measure the magnetic field in your component. So this is also a pretty cool technique. So now, focusing back to the subject of this presentation, so image processing using digital radiographs. So what is a digital image? It's a 2D function, and that function has a given number of rows of pixels and columns of pixels. And what you measure is really the detector response, which is a matrix. And here I zoom in. Sorry, this has moved a little bit, but I zoom in inside our target. So this is a resolution mask we use to measure resolution of our detector. And you can see when you zoom in, you definitely see that it's pixelated values, that they change across the field of view. And in this case, it's a 16-bit data. So you can have values between 0 and 65,535. So in this case, you have a 4K by 4K image, but nowadays the chips are getting much larger than this. And really what you want to do with the digital radiograph is be able to extract information, whether you're trying to measure a defect, the size of a void or a fracture, or you're trying to see changes, in a furnace or, in an environment. The digital capability is really good for that. So first, you have to understand the detector's response. So it's important, I would say, to do light testing with the digital detector before you put it in an X-ray beam, let's say, because you need to know how the detector functions outside of the radiation you're going to expose it to. So here is a 2-bit grayscale. So these detectors don't exist anymore. So or I haven't seen them, at least recently. So you have 4 possible grayscale values. Then you have the 8-bit grayscale, where you have 2 to the power of 8, so 256 values. And then you have the 16-bit, which is the most common, at least in the field of neutron radiography. And you have these, a much larger scale of gray values. So the more gray values you get, the better separation you can get between your data. So here I'm just plotting the gray value from bottom to top in these 2 cases as a function of the position of the pixel. So although they look very similar, you can imagine that you have a lot more capability to separate grayscales when you have a scale that is much larger than for the 8-bit. So I wanted to point out something that is an increasing challenge is the data size and data size and rate at which we measure, because we're usually using digital sensors such as CCDs and CMOS detectors. They tend to have larger and larger sensor size. So here I'm plotting the number of columns on a sensor as a function of time. This is actually cell phone technology chip, and you can see it's growing exponentially. And if you look at the number of pixels even, it looks like a faster growth than an exponential through the year. So anytime you do digital imaging, you should prepare to store and process large amounts of data, which is quite, a challenge, if you don't have the storage space. And an example for our facility, so this is what we expect. So is we're starting with a detector that is manageable, but as we're going to go through time and we get the new generation of detectors, this is the 10 peaks detector here. You can see that already 200 megabytes per second is a challenge, but in the future, because we can tile these little detector chips, then we run into huge bandwidth and data storage issues. So this is something we're taking a close look at, and it also impacts digital processing, because the bigger the data set, the bigger the computer you need to get, or you have to wait longer. So that's the trade-off between the two. So what is digital image processing? It's the ability to use a computer algorithm to process a digital radiograph. And process can mean, it's very broad. You can apply an algorithm to your data, such as a filter, segmentation, feature extraction. You can denoise, you can sharpen your image, you can use pattern recognition, machine learning. So there is a very, very broad range of type of algorithms you can use for digital image processing. And you can apply these algorithms to two-dimensional or three-dimensional, or sometimes four-dimensional. So 2D would be a radiograph, 3D would be a computed tomogram, 4D would be several tomograms through time that you would compare. And that's something we actually are doing as part of a recent project. We are reconstructing an object in 3D, and we're comparing two CT scans that follow each other. So what we do is we add data to the CT, reconstruct the data, and compare it to the previous one. And once we've reached our convergence parameter, we know that adding more data or scanning more of the object is not going to give us more information. So this is a project we have where we are heavily using machine learning capabilities, because we're trying to do this fast, and we're trying to control the instrument and guide the instrument what projection should be measured next. And an important point is you have to make sure that you're not harming the information or removing the information by over-processing, because it's easy to try to get the best processing and the best looking data set. And it's okay for visualization, but if you're doing quantitative analysis, then you have to make sure you haven't drastically changed the information you just measured. So another point is that it's essential to record your steps, because if 6 months from the moment you did the processing, you want to come back, you have a similar object you want to scan, then it's good to have as detailed steps as you can, because it will trigger your memory, and you'll remember what you did. And more often, I actually create a dummy radiograph, and I create the radiograph to adapt to the question I have or the processing I want to do. And I will show an example. And these are very helpful, because these simple radiographs, you can anticipate what the result should be. And then it's the best way to check that what the tool you're using is doing what you expect it to do. So here are a couple of radiographs I created. So these are 16-bit 20 by 20 pixels size. And you can see in the first one, I created the columns with different colors. So there is a gradient, so different contrast. And here it's random. And I use Fiji, which is a open source code, which is basically ImageJ. You may be familiar with that, to create these radiographs. So, and I'll show you an example when I use them and why it's important to use them. So when you plan to do some image processing, you have to have a strategy and a workflow. So the strategy even starts before you do the image processing. You have to understand at the measurement level what it is you're measuring. What is the question you need to answer, and what is your measurement strategy? And in research, we tend to make objects or sample the best we can, so we get the best measurement possible. However, in industry, you are given an object that you need to non-destructively investigate, and it's not necessarily the ideal controlled lab experiment. So you have to spend some time thinking, okay, how do I optimize the measurement? Do I have sufficient spatial resolution? Will I have enough contrast? How about the overall transmission? So you have to think about all this and try to optimize the measurement itself. And really the goal is to acquire the best possible data set you can. And it's always better if you have a great data set than try to correct using extensive image processing after the fact. As I mentioned, you also need to understand what is your objective, what it is you need to know about the data set, what is the question you're trying to answer with the processing and analysis steps. And what tools do you have, to apply to your data to try to get that information? And something I usually do, I go on Google and I check if somebody has developed the algorithm or has encountered the question I want to answer with the data set. And then you need to have a good understanding how to optimize the image processing and analysis to get results that you can be confident about, that you know are true. So for data processing, there are 3 ways to think about this. There are probably more than 3 ways, but one way is to use software that does the image processing for you. And there are open source code like ImageJ, as I just showed you. MATLAB is another one. Scikit, which is Python-based, is another one, which is open source also. You can write your own algorithms in the language you prefer, which, in my opinion, gives you the advantage that you will understand the algorithms you are implementing because you're writing them and testing them. Or another option is collaborate with people in the field who can either develop or share the tools or adapt the tools they have to help you do the processing. So example number 1, we're going to look at the CT scan done with X-rays of an insect. In this case, it's a cicada, so that happened to die in my backyard over the summer. So I just kept it. I froze it in my freezer, and I kept it until I had the opportunity to measure it with X-rays. So here, as a demonstration measurement, so here is the X-ray beam. Here is the bug in a plastic container, and you can see here the detector. So when you do a CT scan, ideally you want to obey Nyquist sampling theorem, which tells you more or less that the total number of projections should be 1.5 times the number of pixels across the sample thickness. In this case, I should have collected 722 projections. However, time is always the limit, and because there's a ton going on at these facilities, so I only use half of Nyquist sampling, more or less, and I collected 401 projections between 0 and 360 with a 40-second exposure time. So why 401 and not 400? Because if you use 400 projections between 0 and 360, after you pass 180, you're going to duplicate the projections. You're not going to increase sampling. So you always want to have a stepping angle that is not, that the number of projections cannot be divided with. So you basically, what I mean is, if you go from 0 to 360, you want to make sure then your sampling is unique even after you pass 180 degrees. Another strategy, and something I've been using more and more, is to use the golden ratio scanning method, which basically randomly sample across the object. So it's turning around the object and randomly sampling, and then it's adding more and more and more. So here's the radiograph showing the cicada. So you can see, we can see with the X-rays the insect really well. We see the edges of the sample holder. And although this says it's 16-bit data, when I pull that with radiograph with image J, then I plot the histogram and it only goes to 85. So it really looks like at that point I collected 8-bit grayscale data, which for this example is fine. So why is the histogram important? When you look at the radiograph, you want to know what pixel values matter to the image processing you want to do. For example, the background has the highest pixel value because there's nothing in the way, so the transmission is the highest. And then you can see the holder here. That region of the holder is next. And then there is an overlap between the bright regions of the bug with the holder. So that's always a challenge, especially when you start doing segmentation, because you want to separate the pixels from the object, and you don't want to grab the pixels from the holder at the same time. So we'll talk a little bit about segmentation techniques, but that's the challenging part, because the darker area are very easy to separate from the rest of the image. It's these areas that look a lot like the holder that are going to be a challenge. So, and the reason why we do all this visualization and understanding of the histogram, it's because we want to be able to look at this cicada in 3D and separate it from the rest. That is not what we are interested in. So we did this, and you can see here, I will show a few sizes that correspond to the reconstruction. So the process workflow of the image processing in this case, after you collect your data, you do the normalization, then you do the reconstruction. In this case, we use filtered back projection. Then you visualize the slices. So you have the reconstruction gives you all the slices, and you can see here I chose the eye region, but you can see, you still see the plastic chamber, and everything else is more or less background. And once you have the volume in 3D, which is shown here, you can do some analysis. For example, I could be interested in measuring the size of the abdomen, the eyes, some internal organs, whatever the science question or technical question is. So when you do reconstruction, you usually get the whole field of view. And as you can see, this is quite a bit of data, a total of 15.6 gigabytes, which you have to carry. As you're doing the processing, the more pixels, the longer the processing will take. So it's always a good idea to crop. So to take a region that is much smaller and limited to the region of interest, and just remove all these pixels that just really don't serve any purpose here. So here is the size of the top view, and you can see some of the cavities. This is the abdomen region, and we can even see here the wings, which are at the bottom, and where the contrast is quite close to the holder itself. So now we're going to talk about rebinning. So rebinning is interesting way to process your data because it increases signal to noise, depending on how you rebin your data, but you pay the price by losing some of the spatial resolution. And there are cases where we have very large data sets and we just can't handle them unless we rebin the data. But you have to determine where is that balance, where is that trade-off, how much of a rebinning can we accept before it becomes a problem. So you can see here, as you bin 2 by 2 and so on, your image size decreases and the overall size of the image decreases. So as I said, it's a balance between what you're willing to lose in spatial resolution and gain in either signal to noise or the size of the overall radiograph. But the most important in any image processing that you do is to have a way to be able to compare what you started with what you have in the end. It can either be a line profile, the histogram, a region of pixels that you look at the values, or the comparison between signal to noise. So signal will be a region in your sample, noise will be outside, and you compare the two with the processed data. So here is the example in this case. So we were looking at maize roots, and we were interested in understanding the dynamics of the water uptake of the roots from the soil. And the challenge is these data sets are really large because our sample chamber is very large. It's 20 by 20 square centimeters in field of view. So we take several radiographs that we stitch together, not in this example, but I will show you an example where we do. And then we need to at least determine, as we're doing the measurement, how we measured enough, do we need to acquire longer? So it's nice to be able to do some processing as quickly as you can, which would, trigger the need to bin the data. So I'm going to go through a few binning options. So here's the 2 by 2. So really, if I go back, we don't see much change. Here's the 4 by 4. We still don't see much change. We can start seeing a little blurriness in the 8 by 8, but we still see some, we still see these roots really well. And here's the 16 by 16, where, I think you will agree that it's very blurry. And if I bring images together, the no binning and 4 binning, you can see these finer roots we can still see. And so what I did for this presentation is I took a region of interest and I applied it to every image, and I looked at the histogram. And when I look at it, at least visually, I don't see much change if I do no binning or 4 by 4. So you could reduce your data size drastically and process your data faster with a 4 by 4 binning. But if I go to 16 by 16, you can see I start losing some of there's a very tiny root here, and it's almost completely disappeared there. The granularity, all the grains in the soil are completely washed off with the 16 by 16 binning. It's very blurry, which tells us the spatial resolution has been compromised or is much lower now. If you did like an edge function measurement, it will be a lot worse than in this case. And when you look at the histogram, all the details of the data you had in the first place are basically gone. It's a very rough histogram. So you can see, even with the naked eye, you can see that 16 by 16 is a little bit extreme for binning of these data. And as I mentioned, we have very large data sets. So this is 1.5 10 to the minus 9 pixels. So it's several radiographs together. It's actually changing as I'm talking. It's the plant is uptaking water, so it's drying the soil, and you can see the stem has turned blue. It was green in the beginning. And so something else you can do with processing is put color to your data set, especially if you're looking at something that's changing with time, so a dynamic data set, because it's very easy to understand and explain because you have guided, basically colored indication where you should be looking. So it's going to take a little bit. That's a pretty heavy slide, so it's going to take a second or two, I think, to change. Okay, here we go. So here is the original sample, which what we did. So this is done after the experiment, and we clean up the soil. We washed a sample, and we determine the size of the roots by scanning them. So another imaging technique. There are specialized scanners for this type of research. And what we designed the experiment to do is to have finer roots on one side and coarser roots on the other side. And this is a mask. So this is another processing technique where you create a mask from your radiograph, and where everything you're not interested in will be multiplied by 0. So that will go away. It's all the dark areas. And everything you want to quantify is 1. And once you apply that mask to your data, you're able to measure anywhere the amount of water in this case. You're able to quantify what is happening in your sample as a function of time. And here we're comparing the left side to the right side. You can see after that, it's easy to measure water content as a function of the distance from the root and as a function of time. So the time is over a couple of days. And you can see the behavior of the left side compared to the right side. So you can really get very impressive and unique information from your data as you do the processing you need to do. But the science question here was, how is the left side or the finer roots behaving as compared to the coarser roots, and how is the water uptake profile compared? How can I compare the water uptake profile, which is what you're seeing here, and understanding the behavior of that particular plant. And this was done after drought. So these plants tend to behave differently after a drought, I would say, period. And the researcher wanted to understand, is there any chance the larger roots would hydraulically redistribute water to the finer roots? So this is something that we have published, and if you're interested, the paper is in here. Example 3. So now I'm going to use these images that I made, the dummy, I call them dummy images, test images, and I'm using the random image. And what I'm going to do is apply the median filter, which is the most popular filter we use. And it's the reason for that filter that we consider most popular in our field in neutron radiography. It's because it's really good at removing hot and cold pixels. Hot and cold pixels, you probably know what that means. A hot pixel is a pixel that is completely saturated, and a cold pixel is a pixel that did not respond, so it doesn't read, it reads 0 or none. Sometimes you will see none NaN in your data because it just hasn't read anything for some reasons. And the reason why we have gammas in our neutron measurement is because neutrons, when they interact with matter, they tend to produce gammas. So that's why the median filter is a very good filter for the analysis processing we do at our facility. But what is the median filter? So the median filter basically takes that center pixel here, and here I selected a 3x3 selection, and it lays out all the values around that pixel, and it's going to take the median. So it's going to take the median between, you know, when you have all these values together. So the M value has to be greater or equal than the second half. Sorry, in the middle. So let's say you have 11 pixels, it will take the one in the middle, so number 6. So it's not ideal for random noise, and you can see here, you could you know, assume this is random noise because I can't see my radiograph or object. It's the advantage it has, you will have less blurring than a smoothing filter. So if you have very spotty pixels, the median filter is the best approach. So what I did here is I basically wrote down the values that are on that image, and then I listed all the values, and the median has to be on the second half, the slowest value on the second half, if you have an even number of values. And what it does, it just replaces that pixel with that value. So what you did here is basically verify that your algorithm is doing what you expect it to do, which is an important step to take before you apply anything to your data, because you don't know what to expect. In this case, we know what we should expect. However, it's very easy to say, oh, well, you know, I have so many pixels that are hot and cold. I'm just going to apply the median filter to the whole data set. So in that case, you can see how drastically you've changed your radiograph, because it's not applicable on the whole image like this, because this is basically random noise. You can't apply median filter to random noise. It's really for these specific pixels that need correction. And the way to compare them, let's say your both radiographs don't give you enough detail that you can see the difference. You can always plot the histogram, and when you see a histogram that started like this and became that, then you know, okay, something is off in my data set. I really need to see what's going on with what I'm doing. And then I chose the other dummy radiograph to show you that you can apply a median filter, and in some cases it doesn't change anything, because in this case, because I'm looking at columns with the same grayscale, and a 3x3 median basically means the value stays the same, because this will be the value in the median. So if you don't see anything, it may not mean the filter is not working, or the processing you're doing is not working. It may actually mean that it may not be sufficient or appropriate for what you're trying to do. And now on a real data set, so this is a turbine blade made by additive manufacturing. So it's Inconel 718. And we did a scan, and because it's metal, neutrons will generate gammas, or the part will generate gammas as it sees the neutrons. And if I zoom in that area, you can see all these hot and cold pixels everywhere. And the goal is to be able to assess the inner airflow of the turbine, and for that we have to have pretty good data so we can map, and create a step file that companies can use to compare with their models, for example. So how do we clean this data? So we can apply a 3x3 filter. So you can see it gets better, but we still have a little bit of pixels that are problematic. Then we go to 5x5, it gets a better, the median filter. And then I can be a little extreme and say, okay, I'm just gonna do 21x21. And the background looks very smooth and nice compared to the 3x3 median filter. However, if you look at here and then you look here, you've lost a bit of information. So you've really blurred out the details inside the sample, which is not ideal when you're trying to look at the details inside the sample. So how do you pay attention to this? Let's say you have a lot of images or your image is very large. Let's say you're looking at a component from an airplane and you cannot go in sitting down, spending hours comparing the two like this. So what I do, I have a simple trick. I divide the original image by the processed image. So the original divided by 3x3 gives me this. And by looking at it, I say, okay, it really cleaned what was in the way. Maybe a little bit of these hot and cold pixels were within the sample. And then you do the same with the 21 by 21. You start seeing the sample. You actually start seeing the component part and the number it has, and then you realize, okay, clearly something is off. I'm over processing the data, and maybe I should back off a little bit. So that's a very quick way. You can do this in Imagery. You pull the two images and you just do the ratio, divide one by the other, and you can see this. So now I'm going to talk about visualization, which is an important part of processing. So when you do data processing, you want to be able to, as you go through your workflow and steps, you want to be able to visualize what you've done, right? You don't want to wait the final step and visualize and then realize the results are nothing like you expected. So visualization is tricky. If it's two-dimensional, it's manageable. Three-dimensional becomes a little more complex. And for three-dimensional visualization, very often you're going to need segmentation, where you pick and select different areas of your sample and make them appear and disappear, cut through your sample non-destructively, so virtually, and see, take some measurements or measure a fracture or void or a defect. So here I'm using a sample that is a demonstration sample. So this is a brass sundial. And this is a picture of it sitting next to a quarter. So it's about 9 by 9 centimeters. I've removed the plastic because neutrons cannot go through plastic. And what I was trying to demonstrate here is, first I'm going to do the reconstruction. Then I'm going to visualize all the pixels in the reconstructed data set. So a huge data set. Then I'm going to use the most simplest segmentation technique, which I'm going to look at the histogram and separate sections of the histogram. So first, what I do is I look at the 2D histogram, like we discussed earlier, and with the cicada, and then I determine which pixels belong to which part of the sample, which ones are the background, because when I do the thresholding method, then I need to know which pixels to choose. And then you can start doing some of the virtual cuts or some analysis or further filtering, processing that you need. And you can go back and forth between the two and convince yourself or feel confident that what you're doing is correct. And I mentioned here that there are very advanced segmentation techniques that are available, which you might need if you're doing very precise or detailed quantification. You may need to kind of add a more complex segmentation technique than this. This is the most common. This is the simplest one. It works sometimes, and sometimes it does not. And I'm going to show you what happens to the sample, the compass here. So here is the visualization of the complete data set. So it's basically 2000 pixels by 2000 pixels by 2000 pixels. So this is everything. So this is the whole histogram from 0 to 65,535. And these are two different views. This is visualized using a commercial software called Amira. And then I use the histogram-based segmentation. So this is a thresholding method I was talking about. And it does okay, but not great. You can see there is some leftovers of the background here. I'm not sure what's going on there. You know, it's you're visualizing it here. So there definitely is some segmentation technique that could be implemented to improve the visualization. So usually what I do is I will go in the 3D data set and I will label. I will label with a given color the pixels. So it's time consuming if it's a large object, but if all you want, let's say you want to map the porosity inside a component, you could try to see in the histogram what values most porosity voids have, and then label all these values with a given color. And the advantage of the labeling is you can turn them on and off. So for example, I could turn off most of the sample and let's say just keep this you know, in the view, and then do some processing or some measurements with the tool after everything else has disappeared. It's especially very valuable if you're looking at something inside. So if you're looking at something inside, you want everything else in your way to disappear, which is really the power of non-destructive investigations that we do every day. And here, what I did is a cut. So the advantage of using 3D visualization tools is that you can look inside, you can select an area, you can play a lot of neat tricks. But I would say 3D visualization and analysis, that's another level of complexity. So when I do a 3D-dimensional analysis, I actually use the slices. I don't necessarily work directly with the volume because I do the image processing on the slices. And then when I'm happy with the image processing and I've removed background artifacts, you know, all the problematic noise I see, then I load the object in the 3D dataset, 3D visualization software, and then I start doing some analysis. You know, what are the root sizes in the plant? How much water is moving? So I do this after I'm done with the processing. So, and some people, they do a lot of data processing during, you know, with 3D data, which, you know, kudos to them. It's quite complex to do. So a few software and reading suggestions. So I actually have the book. So that's a book I can show you guys. I have with me almost every day. It's the digital image processing book that is done by a couple of professors at the University of Tennessee. I mean, there are a lot of books out there, you know, you can find. And it's a really nice, you have to have basically a place where you can go and read about the algorithms and try these algorithms. So this is really the book to see what these algorithms do. And then this is ImageJ. So there is a little book, ImageJ, you can get if you're interested. And ImageJ, as I mentioned, or Fiji, has a really nice interface, very easy to use. It was developed by NIH for the biomedical community, but you can use it for any type of radiograph. And Fiji, which is what I use, is ImageJ, but on steroids, because it has all the algorithms developed by the community. And most likely, you know, I would say 95% of the time when I'm trying to do something, someone else has already figured out how to do it. So if it's not on ImageJ, it may be on a Python script, or, you know, somewhere I can find in the literature and reproduce the algorithm. So ParaView, VolView are visualization software, 3D slicer also. The Astra and TomoPy algorithm are used for reconstruction. And then the Python Jupyter notebooks, which I think are excellent. If you're not a programmer, it's a really good way to get things done very quickly and neatly, because it shows as a digital notebook, and you have these cells. And in each cell, you can put the algorithm and test you want to do. And it's instant reward because you can plot the radiograph before and after. You can see it as it's happening. And then you have a commercial software. So Octopus is for X-rays, MATLAB, VG Studio, Amira, and VG Studio and Amira are visualization tools. Octopus is reconstruction. Actually, there's a new commercial software I just purchased called X-Act, and it's feedback projection reconstruction software. So this is what a Jupyter notebook looks like. So you see you have these cells with the code you've written. You can add a little bit of information of what your algorithm is doing. And you can plot your data or your radiographs. You can build a general user interface on top of it, so you never have to deal with the code and just process your data. And here you see this is the sundial compass that we were looking at a few minutes ago. So this is just a raw radiograph where you're looking at the histogram in one direction. So in summary, I want to say that if at all possible, and I know it's difficult in the field, but try to optimize your experiment, because it's much easier to work with data that have little background and noise than it is to have to deal with the processing after the fact. And also, even before you optimize it, you have to understand, okay, why am I doing this measurement? What it is I'm trying to get out of it? How do I know, what algorithm to use before you do the processing? So are you looking at a defect, some leak somewhere, the strength of a material, the microstructure? And then everything I do, I need to understand what is the question being asked before I can do any processing, because it really drives what you're going to do with the data. And also a test radiograph is essential. If I'm using an algorithm I just wrote, or I'm using someone else's algorithm, I want to test it with a data set that I understand and I know what the answer should be. And that's because I want to convince myself, okay, this is doing the right thing, so now I can apply it to a more complex data set. And there are very different levels of digital image processing. And frankly, I'm learning every day. So I would not call myself an expert, more a student, because every problem I work on has a unique requirement or workflow for image processing. And what you do as you learn all these tools is you have basically a bag of tools or algorithms that you use and you apply and you adapt to the technical or scientific question you have. And then, of course, there are more advanced segmentation, analysis and processing techniques, especially when you go into quantitative analysis, which is really the power of digital image processing, is you can quantify what you're seeing because it's a digital image and because you have numbers. These are matrices. Image processing can be biased, and the best you can do is keep track of your steps. That way, if someone else say, hey, I'm getting a different result, you can share what you did and they can follow your steps. And visualization, as I said, is very important because you can go on and on and on and do several steps, and then you get something very surprising and you're not sure, okay, where is the breakdown? Where did something not follow what I was hoping it would follow? And I want to acknowledge the whole imaging team. I have the pleasure to work with my husband, Jean, Yuxuan, Eric, Venkat. So Venkat is our reconstruction expert. And if you guys are interested in reconstruction, algorithms and techniques, he's really one of the most knowledgeable people in the field. And he's doing a lot of artificial intelligence, machine learning development for reconstruction that are really, really cool. For example, we were measuring a battery at the beamline, and we were able to, in 12 projections, so only 12 angles, to get superior in terms of signal to noise data reconstruction. So the volume itself looks so much cleaner using his algorithms than the filtered back projection, which is the most common and fast reconstruction technique. Shimin is our postdoc. Harley also works with us at the beamline. I also want to thank DOE Basic Energy Sciences, who sponsors the user facilities, the special nutrient source and the high flux isotope reactor. And all the colleagues, at DOE, ERE, and the RNL manufacturing demonstration facility, which they provided the turbine blade sample that I presented in the slides, and of course, colleagues at Oak Ridge, ASNT, and colleagues from other facilities, including the academia and industry. And this is it. So if you have any questions or comments, or you want to discuss something, I'm very happy to take any questions or comments. It's 1 hour on the dot almost.
Oh, very good, very good. I was gonna say, feel free to type in your questions. You can put it or in the chat. You can put them in the Q&A box if you prefer, or raise your hand and you can ask them directly. Well, while we're waiting for others to, we have any have any other questions pop up? Let me see here. I'll let Karen keep up with that. But
Yes.
I was kind of worried, thinking about the Python software. I've not worked with that. What's the good way to get started with Python?
So Python is a fun language to learn. It's very intuitive. And what you can do, I think I'm still sharing my screen, right?
Yes.
Yes.
Okay, so let me go. You can go on Anaconda, which is you can download Anaconda, which is the Python environment.
Anaconda?
Anaconda. You go on anaconda.com. It's an individual license, which is open source, and you can download it from that website. And I actually have it on my computer. Let me load it and show you what it looks like very quickly. It's a really nice interface that exists on PCs and Mac computers. I'm not sure about Linux, but it has all the types of, I was talking about the Jupyter notebooks. So this is what it looks like. You can launch one. And I will just create a new one. And it looks like this. And you can type, x equals 2, whatever, print x, you can,
We're still seeing your presentation. I don't know if it's amazing.
Okay. Let me try to share my desktop. How about now?
Yes. Okay. Now I see it. Mm-hmm.
Okay. So you can create. So let me go back. So what I did basically is I loaded Anaconda. So the software I was telling you about, if you go on anaconda.com, sorry, you can get for free an individual license, and it will look like this, which is what I loaded on my desk, on my screen here. And I use Jupyter Notebook. Some people prefer to use the Jupyter Labs, but really the nice thing about Anaconda is that you have a learning center that has everything that you want to do. It's very powerful. So you can start with just the beginning, learn Python. You have tutorials for beginners, and then you have the normalization. I mentioned SciPy, which is for images and numerical digital processing, basically. You can learn about this, and you can go in any of these. Let me see, I'll go to Matplotlib, for example. And it really a step-by-step guide, they say, okay, write this in your cell and you should see this. And then, the next thing to do is go here and try this. So they explain to you what the code does and, what the terminology is and how to write things. So it's really nice. And you can get very advanced with Python if you choose to do so.
It looks pretty good. I've used Fiji a few times, quite often. It's just
Yeah.
haven't gone to something as advanced as this. It looks that'll be good to use.
Yeah, and it's free. And the advantage of it being free is that if I develop a code, if you tell me, here's my image and my algorithm doesn't work, can you take a look? I can take a look. You send me the notebook. I can add to it or modify it, and then I can send it back to you because it's open source. That means there is no copyright or anything, that I need approval for, that would make this a very long process.
Excellent.
Which is why, so we tend to lean toward open source, languages. So it's much easier to share and collaborate.
Excellent.
Sure.
So in the comments, I've got a very good presentation. Yay.
Thank you.
Very nice.
I also have a question. Are you involved at all with ASTM?
No, I signed up 1 year and I could not it was pre-pandemic. And I know one of us is Aaron Kraft from Idaho National Lab, is very involved in ASTM, and he did ask me, can you join? And I just can't find the time. I'd love to be involved, but I'm involved with ASNT, but not ASTM.
We're going to have to work on you.
Okay.
Okay. Another question that we have is, have you done some DR comparisons of 14-bit versus 16-bit detection systems?
I do. So the microchannel plate I was showing, with the huge data rate increase, it's a 14-bit detector. And I have very rarely seen a big difference between 14 and 16. A huge difference between 8 and 16, but 14 and 16, at least for the objects I looked at and the analysis I've done, it was not a huge difference.
Okay, a couple more comments. Excellent job.
Thank you.
And, thank you for the presentation. Another question. Do you have a preferred filter that you regularly apply?
It depends. So I'm like you. When I have a object, when I have the digital radiographs, I will do the median filter because it's the most common, especially if I have this, hot and cold spots. But then I try, different filters, maybe a smoothing filter, a Gaussian filter, and I do exactly what I showed. I compare the radiographs, because if I'm starting to change most of the radiograph, then it's not the right approach. And sometimes the noise is just too much, and you end up plotting data with very large error bars, which in journals the reviewers don't like, and they always want you to go back and do something more. But sometimes the data is just not ideal, and you have to accept it.
Okay. I have a question that says, can we get the slides? Not currently. Not currently. We are recording it, but once Hassina has all of the paperwork finished with the National Lab, then we will have them available on the Ghostrock website.
Yes, absolutely. Yes. I'm just waiting for approval, and everything I do is publishable, so there shouldn't be any problem.
So more to come, more to follow. Thank you. Very nice format and examples. Another question. Are there particular materials and shapes, such as Inconel turbine blades, that are difficult to scan?
Yes, so neutrons are very good at going through metals, but there is a limit. So thick metals like steel, we can go through maybe 1/2 inch to 1 inch of steel. After that, it becomes a problem because and also because we have a spectrum, which I could cover in a future presentation, is how do you correct for beam hardening? That's a big problem with neutrons. I know it is with X-rays. So there is a limitation. So we have a tool I can show you. So sorry of taking going back and forth, but let me share my screen again. We actually have a tool with neutrons you can use to calculate transmission. So it's called NEUIT. I don't know if you can see. It's NEUIT.sns.gov. And you can go here. So this is one of our beam9. Let me make this bigger. So you can calculate neutron transmission and say, I want to bring a sample that has 10 millimeters of water. What is going to be the transmission? Oops, I think I made it too big. And you submit. And I'm going to make bigger again. And it says, okay, well, the transmission will be 6.5%. Terrible. You always want to stay above maybe 20%. For CT, definitely 20%. But you can say, I'm simulating steel with just iron. I'm just bringing, let me remove the density here because it's not one. Oops, I will lower this and move this. So I'm just trying to remove the density of just pure iron, and I submit, and I get through a centimeter 26% transmission. So it's a nice tool to, kind of guesstimate what you want to measure. I'm sure they exist for X-rays. You can add lines. You can say, I have in the beam 10 millimeter of iron, 1 millimeter of copper, whatever the material you're looking at. Inconel is mostly nickel, and then you have the other elements. The only, I would say, challenge with neutrons is activation. So unlike X-rays, samples can get radioactive, not to the point that you cannot handle them with your hands, but they can get radioactive to the point where it's difficult for us to ship them back. I mean, we can ship them back, but they have a radioactive tag, so which means you have to have a license to receive radioactive material. So in that way, I was told by an industry collaborator, then neutron radiography is destructive because they don't get the component back.
That's a point. That is a point.
Yeah.
Okay. Reverting back to the earlier question about, are you involved with ASTM? Oh, I've just lost it. It says, when you shifted screens, it just blew mine up.
Oh, sorry. I'm sorry.
We have the comment that it would be good for you to be involved as we need to create a specification on filters used for industry.
Oh, yes. Yeah, I'll be happy to. And ideally, we should have example data, that we can maybe not attach to the standard, but, website or somewhere people can go to and say, when I use this filter, this is what I should expect.
Well,
I don't know if it's possible with me.
If you will work with whoever's interested in working with you and putting that together, I can promise you I'll put it up on the Ghostrock website so everybody can see it.
Okay, great.
Okay. And of course, we have another one that says, yes, for sure, I ditto camera sentiment, and that was from Trey. Another question is, do you regularly apply binning as a standard process? If so, is 2x2, 3x3, or other?
I do usually 3x3. And I usually do binning because I need an answer at the beam9 so I can make a decision. And usually we have access to these facilities for a couple of days. and the measurement will last a couple of days, but I need to know, like in the plant example, do I need to add more water? Is the plant dry enough? What's going on? So I need to be able to look at all the data in a pretty quick manner. So it's very complicated if you don't bin your data and you're trying to see almost, I would not say real time or live, but within half a day, you want to know, am I going in the right direction, or is this plant not behaving the way I expect it to?
Okay. Well, that's the questions that I have in the chat. Remember, if you have a question, to put it in the chat box.
And I want to say image processing can seem overwhelming, but
we all discovered that, Hassina. I think we all.
But or programming for that matter. But when you start with a problem you're trying to solve, it's much easier because you're very focused. Trying to learn Python just as a general tool it's quite complicated. But if you say, I want to do this with Python, where do I start? It's very encouraging because Python is something you can pick up very quickly and get results, within a few days. And it's because we do imaging, it's instant gratification because you do something and you see the results on the same page and say, oh, okay, this is what this does.
Yeah, so what I would like to know is this, what methods can be used to reconstruct sparse data? If you're missing angles or you have a strong attenuation in some angles, things like that.
So, so for sparse data, let's say you have a component where some angles are very dark because the radiation does not penetrate enough. You can use iterative methods, and these are quite advanced. They are open source code to do that, but you need a pretty good sized computer. You can't do this on a laptop. Because the fetal back projection is the most common. It's what you get at the doctor's office when you do a CAT scan, because in seconds you have the reconstructed object. The iterative reconstruction, unlike fetal back projection, works in real space. Fetal back projection, you go in Fourier space, you do a Radon transform, and in frequency space, things are much simpler. When you go in a real space and you try to connect the dots between projections, that's when it's become more complicated because you have a very large number of equations with a very, very large number of unknowns, and you're trying to converge to a solution. So that's a computer intensive, but that usually is very forgiving if you're missing angles or signal to noise is not ideal. That's the best reconstruction you can get.
Okay, well, that's what I've always been kind of afraid of with, not the unknown, fear of the unknown, which I think we've all gone through at some point in time. Image processing is, as you said earlier, a little overwhelming to most people, especially in the beginning. Okay, well, are there any other questions or comments? Because the chat line is open. Now, everyone on this line, George and I especially, have heard that Hassina is willing to talk on more detail on subjects in the future.
Yes.
I wrote that down.
That's fine. So if anyone has a specific subject on image processing or analysis or reconstruction, they want to us to dive, do a deep dive.
Okay.
I'm happy to
well,
help.
I would like to circle the wagons on something that we were talking about yesterday and no one else was hearing. But you were saying that if someone has a specific problem that they can work with you directly. How does that work?
Yes, so if you have an image processing question or problem and you are able to share the data with me, I'm happy to collaborate with you. The challenge is it would be good to make the data public so we can publish them and also present them at one of our seminars so everybody can benefit from the development. So that's the only, I would say, not drawback, but because I'm paid with the taxpayers' money, so I have to give back to society, right? I can't just help an industry or collaborator and nothing comes out of it.
So essentially, if they want to get to you into Oak Ridge, they have to go in with the eyes wide open that this is going to be at the end of the project, a published work.
That's what I prefer. There are ways where we do full cost recovery, where you would come as a, with an NDA or, an agreement with the lab, and then we work on data, and then the collaborator leaves with the information, everything. We don't keep any record.
Okay, so
that's above my head. So we would need to involve, more people, and it will take quite some time because there's some, I guess, the non-disclosure agreement, for example, it goes back and forth between the lab and the company. And
yeah, I've worked with non-disclosures with the national labs before. It is a process. But there is a way to do that if someone has a very closely held proprietary project and they want to involve and get you involved and collaborate with you. There is a way that they can do that without publication. But if those constraints are not there, they just have a problem that they need solved, and they need solved rather quickly, then with the idea that the solution would be a published article then, or video or whatever, that,
yeah,
that's okay. So,
and I've published with industry. Sometimes I can publish on the object itself, but not the application or the material details, So there are things we usually find a way to publish.
So it's a case by case thing.
Exactly.
But the important detail is you can help people solve their problems.
Yes, so that's what I'm paid for. That's what I'm paid to do. So.
Well, and you have the full resources of the National Lab and the team that you work with, who are just stellar.
Yes, we have very good people, very, very smart people, I have to say. I'm just one small person. There's a huge team behind, and a lot of knowledge, accumulated knowledge over the years. So I always tell my students, if it was simple, we would not do it. So usually when somebody comes to us, they have a big problem and they tried everything and nothing worked. So we usually get the tougher problems, and that's probably why we dive more into processing or the reconstruction or machine learning, is because the easy solution, they would have found out, they would have solved the problem themselves.
I have one final question that I think is going to be, can you put your contact information on the screen? Could you share your contact information? I'm being asked about your email.
Oh, yes, sure. Let me share my screen. So here is my email. Let me make it bigger.
Yeah, make that bigger.
It's my last name, hn@ornl.gov.
Okay, well, let's leave that up for a second, because you have a beautiful accent, but your last name has got all the extra letters for an American that
it's French.
Makes sense for French language, but Americans think there's a lot of extra letters in there.
There is. So my son is 14 and he's learning French, and he does not understand the grammar, and he does not understand why there are so many letters that nobody pronounces.
Well, yes, and that's why years ago, when I first met you, years and years ago, I don't even want to talk about that, but I had to pull you aside and say, please say your last name for me, because I know I'm going to butcher that if I'm trying to sound it out.
Yep.
I also typed Hassina's into the chat box, so if you could, her email address and mine as well, so if you want to copy and paste. Well, I have my
Sounds like my house. Each time somebody knocks at the door, the dogs. Woo!
Oh yes, it's the one thing that COVID has taught us is how to work through background noise that is not normally found in the professional environment.
I agree.
Okay, well, thank you, Hassina. This is Dr. Hassina Bilheux from Oak Ridge National Laboratory, and she was kind enough to come and be our first ever Ghostrock panelist. we are going to try to put on a Ask the SME or some kind of topic for digital radiography monthly from Ghostrock. You will, I've already got her promise. I'm going to retread Hassina with some in-depth discussions. So anybody who's on this line, we're going to come out with, I will be sending out some questions, but if anybody who's attended this would like to see something specific at a future session, just send it to George and we will see about finding a subject matter expert. The intent of this is just to share knowledge and to bring the community closer together with problem solving, knowledge sharing, training, etc. So no topic is too big or too small for us to come up with an SME on it. And since George and I have been in this industry since, longer than breakfast, we have a lot of people that we can get available to us. So send us anything that you want for future episodes, and be looking for next month's topic, which I have not decided on yet, but it will be coming out shortly. Thank you so much, Hassina. It was, as always, fabulous.
Yes, thanks a lot. That was excellent.
My pleasure. Anytime. I'll be happy to come back and present, or even invite some of the team members who have different, expertise areas that may benefit this group.
Excellent. Yes. Excellent. That would be wonderful. Well, thank you for joining us today. We have concluded and are going to conclude, but I will, as soon as I have permission from Hassina to publish this talk, I have been recording it, and I will get it up on the Ghostrock website. So it's full and open to everybody. No one has to worry about memberships or anything like that. It's just the information sharing. So be watching for that announcement coming out. I will probably be putting that on LinkedIn. So thank you so much, and everybody have a wonderful day.
Thanks, you too.